Hi, I'm Zerbe, and I'm an engineering director in the hardware technologies team at Apple. Here's some of my background. Probably the most interesting thing here is I like to juggle. Today I want to cover at least two main topics. First, I want to show you how innovations in circuit and silicon engineering are key to breakthrough products. Secondly, in the mobile space, power is performance. The capacity to deliver performance is driven by the ability to conserve power when you don't need it. If you care about performance, you care even more about power. So we're going to look at Moore's Law and the end of Dennard scaling, and then look at a few techniques for building highly efficient designs. Now, Apple's custom silicon journey really got kick-started in 2007 with iPhone. The original iPhone was revolutionary, but the SoC could barely keep up. And we wanted to do so much more. What this did do was wake us up to the importance of custom silicon at Apple. And so, by 2010, Apple announced its own phone SoC. It had a handful of custom accelerators, freeing up the CPU and making the system much more reliable and power efficient. Since then, the custom silicon design at Apple has expanded across all of our products, from the extremely power-efficient H1 silicon in AirPods to the crazy performant, recently announced M1, M1 Pro, and M1 Max. And all of this world-class performance and power efficiency with the same instruction set. Silicon design at Apple has grown like a tree, with iPhone's A series SoCs as the trunk. Let's have a look at some of these branches, starting with AirPods. The first AirPods were made possible by W1 silicon. W1 was really a feat of analog mixed signal design, delivering great RF performance off a tiny battery, only 1/4 the capacity of others at the time. The mixer-first Bluetooth receiver architecture with passive gain resulted in exceptionally good selectivity, linearity, and noise performance. This crafted circuit design is why with AirPods you can walk away from your phone and not drop the connection, while keeping to incredibly low power levels. W1 also used other radical techniques to achieve state-of-the-art RF performance and an ultra-low power RX. This was critical for long listening time. AirPods also solved another problem with two untethered buds. Normally, two buds without a wire would require forwarding the Bluetooth channel from one bud to the other, consuming twice the bandwidth. But by listening to the same RF source and acting between the two buds during channel idle times, bandwidth could instead be reserved for high-fidelity audio. In 2019, Apple delivered a significant leap forward in user experience with AirPods Pro. Under the hood, AirPods Pro are a whole new system with an IMU, optical ear sensors, mics, pressure switches, and obviously speakers. But with AirPods Pro, we also added a breakthrough level of compute power with H1 silicon you can see on the SIP here. In fact, each H1 powered AirPod has more computing power than 30 Mac Classics. And now you've got that much compute in each ear. This makes for some great features, like great noise cancellation and a transparency mode that works just the way you want it to. Amazingly, because new features are added through software updates, headphones, which used to be a fixed function purchase, are now constantly advancing with new features. And all of this is enabled by custom mixed signal H1 silicon. Next, let's talk about iPhone, at the core of our silicon tree. iPhone has been a story of relentless performance improvement alongside silicon integration of communication, compute, sensors, display, and audio technologies. Some of the silicon systems in the current iPhone 13 Pro that are designed by Apple or our semiconductor partners include broadly RF with 6 different radio subsystems, up to 3 forward-facing and a rear-facing camera with Face ID, a whole host of sensors with custom silicon from LiDAR and IMU to proximity and ambient light sensors, incredibly capable and power-aware display and touch haptic, I/O, power, and audio subsystems. Each one of these is enabled through custom silicon designs with a craft and expertise all its own. And of course, the SoC, with its performance and efficiency cores, GPU and neural engine just for a start. Now let's talk about the Mac. After building our own phone SoCs for a while, folks started to take notice and began tracking our progress. Pretty soon, the trends made it clear what we had to do: bring all that we had learned about building efficient mobile processors to the Mac. And so, in late 2020, we launched M1. M1 has an 8-core CPU up to an 8-core GPU and 16-core neural engine. And for the first time, M1 provides the Mac a unified memory system. M1's unified memory provides a single high-capacity, high-bandwidth memory system that gives the CPUs and GPUs both what they need without compromises. M1 Pro doubles the memory and has a 200 gigabyte per second memory interface, an even larger compute complex. And M1 Max doubles the peak memory size and bandwidth again, and adds even more GPUs and tops the scales at 57 billion transistors. Now, engineering this level of performance is one thing, but the key for us at Apple was doing it in a power-efficient manner. So now let's talk about power and performance and some techniques for building efficient designs. You're probably familiar with Moore's Law, and maybe some people bemoaning the end of it. Here's the prediction and the actual. Notice the log scale on the y-axis. Being off by 1 order of magnitude in 44 years of an exponential isn't too bad. Moore's Law still continues, but at a slower pace. But the real problem is the end of Dennard scaling. Dennard scaling, or constant field scaling, meant that as technology kept shrinking, the power per unit area was relatively constant. This held until about 2006, when device physics made it impossible to keep scaling VT with each process node without leakage power taking over. So why does this matter? Because although we're getting more and more transistors, we can't keep them all powered up the way we used to. Okay, in the big picture, we're getting more transistors through Moore's Law, albeit slower. But the end of Dennard scaling means that an increasing power density, watts per square millimeter. Now, applications want more performance, but battery density isn't increasing much. So system power can increase either without crashing the battery life or bulking up the battery, and either of these would be totally unacceptable. So what's the solution? Custom bespoke blocks with innovative circuits and architectures that are very power efficient for the specific task at hand, and dark silicon. Okay, so let's have a look at how this practically works with a few glimpses into the day of a life of a phone SoC. Here's a simplified block diagram of an SoC. You can see the performance and efficiency, CPUs, GPU, and so on, but also highly bespoke blocks, like the video and audio codecs and the neural engine. Now, the best user experience means optimally running different functions while powering down or putting idle blocks into a deep sleep to conserve energy. Being powered off, these blocks are called dark. Our user might start the day by browsing the web, which is not stressing the system too much, and then switch to photography. Somewhat higher power with the camera pipe, neural engine, plus CPU and GPU all working together to deliver features such as deep fusion and other computational photography. And then maybe switch to watching video using the dedicated video decoder for the lowest power. Then shifting to a high power scenario, 3D games with the GPU and CPU potentially operating at their maximum performance. Finally, shifting to listening to music on the dedicated audio codec. Now, it's important to realize that the SoC is not designed to run all of its subsystems each at their peak performance simultaneously. That would lead to a vastly over-designed device and lower performance overall. Since power is so important, many innovations in mobile SoCs are around power delivery and power usage. How does this work? Okay, for those of us who care about power and chip design over the last few decades, there's been one equation that has ruled them all, CV squared F. This is because historically, most of the power in CMOS has been dynamic switching power. Now, since the end of Dennard scaling, this has not been totally true. There is a DC current component, which is mostly leakage. But how does this work when you want to reduce power? Well, if you reduce frequency when you don't need performance, it gives you a linear effect. But if you reduce voltage at the same time as frequency, you can get a cube law effect with CV squared F. This is great for energy savings in mobile designs. We don't have to consume power when we don't need to. This technique is called dynamic voltage and frequency scaling, or DVFS, and has been around for a while. With DVFS, you simultaneously adjust the frequency and the voltage of the system to minimize the power while getting the performance you need. Applying DVFS to an SoC, you end up with power bands, which operate at different voltage and frequency levels. Here's an example of how this might work. In the zero power state, the SoC is totally off, so it takes some power to get the system to even a standby level. We can call dry zone the level where we're actually doing work. There are also a couple of other low power idle states where you're ready to act or waiting for data, but still not really doing any useful work. We can call those nullstone and millstone. Using our power bands, this is an example of a terrible mobile processor, and you can see why. The millstone and nullstone idle levels are bunched right up against the drystone, so even when you're in an idle band, not doing any useful work, you're not really saving any energy. DVFS really isn't helping here. Our average power might be, say, at this line here. A fantastic mobile processor, on the other hand, pushes our nullstone and millstone levels away from drystone. So some good energy savings can be achieved by going back and forth from active to idle states. By separating the power between the active and idle states, we've been able to reduce the average power and extend battery life. So, how do we get from terrible to fantastic? We want to apply these techniques, but how do we do that without affecting performance? First, we want to reduce the power of the idle states, and this starts with gating. The effect of clock gating is huge, and power gating as well, but also entire rail gating, which eliminates both switching and DC power. NAP memories can also be important for reducing idle state power. The other way to reduce average power, of course, is to reduce the maximum. Minimizing data movement is key, as is trading off wide and slow versus narrow and fast, and sometimes avoiding logic parallelism, which can be great for performance but terrible for energy. There's one more equation, though, that we've made more important by doing all this work. dV equals LDI over dt. All of the switching from high power to very low power is a bit like a bad taxi cab ride. You're going at full speed and then you slam on the brakes. And every power network has inductance. That's the L in the network shown here. And the electrons in that inductor don't like those rapid current changes, the very ones that are giving us the performance and efficiency we need. LDIDT gives us voltage noise, or ringing on the power supplies. In fact, the spiky waveform on the right is from just such a network. These spikes can overshoot and undershoot our nominal operating voltage, forcing us to provide extra margin and wasting power. DIDT continues to be a growing problem with lots of great potential circuit solutions. Okay, so let's see how things worked out for M1. The combination of these and other energy-saving circuit and architecture techniques Apple used with M1 was dramatic. When looking at performance versus power, M1 at launch was significantly more performant than the latest PC laptop chip. In fact, at ISO power, it achieved twice the performance. Perhaps more interestingly, at ISO performance, it only consumed 1/4 the power. You can see here how each performance level effectively spends power with the most efficient combination of active blocks, bespoke silicon, and DVFS for the workload at hand. This great result was enabled by optimizations at the system, architecture, and circuit level, and really shows the potential for innovative uses of the available transistors. Now let's talk a bit about what's next. Across the industry, we're seeing an explosion of opportunities for circuit design and silicon engineering in different spaces, from AI to health, AR, VR to cloud computing, and of course, personal computing. It's really demand for intelligent systems everywhere in our lives that's driving adoption and innovation in silicon engineering. Now, to make a system work, there are many layers of the stack, from physics to the application level. Typically, circuit designers feel like they're in a span somewhere around here. But truly optimizing means knowing what to customize for maximum impact, and this means intimately knowing your application, all the way from algorithms to transistors. Notice also on the stack that the lower layers float the upper layers. Everything above got better when devices got better. But now with device improvement slowing, circuits are doing the heavy lifting. Great circuit design has incredible craftsmanship to it, and the quality of that craft shows up in the key features of the products we use every day. I hope that by joining Circuit Insights today, you'll begin to appreciate this wonderful circuit design community, and even consider joining it yourself. We can't wait to see what you'll do. Thanks for watching, and stay safe out there.